Soil mechanics is basically a branch of civil engineering that uh, predicts the soil performance based on, of course, utilizing characteristics of soil, utilizing the engineering techniques of dynamics, fluid mechanics. In the in excuse me, in the outline you've seen that we are going to talk about, for example, the Darcy's law from fluid mechanics, because this water affects the behavior of soil. So these principles of fluid mechanics as well. We'll talk about. There's also many technologies. We are going to talk about even the dynamics, because dynamics is civil engineering is about static stuff, but also in motion. For example, if there's an earthquake, maybe not in this course, because this is an introductory course, some things may be too complex to tackle at this moment. So we're going to start with the introduction parts, but for sure things like fluid mechanics we're going to talk about. Dynamics may be too complicated for this introductory course, so may not be able to tackle it here, but in other courses in the future, maybe in fourth year, I think fifth year, fourth year, I think technology is 4 years, maybe in fourth years, I think. Soil mechanics includes the study of soil composition, strength, consolidation, and the use of hydraulic principles to deal with issues concerning sediments and other deposits. Soil mechanics is one of the major sciences for resolving problems related to geology and geophysical engineering. And also, please feel free to ask any question if something is not clear. You can ask at any time. So you don't need any prior knowledge of this. This is not to say, it's assumed that you have the basic. You've gone through the high school. There's some basic physics, I believe, and math, and also the first year course you have done. I think you've done some physics, some chemistry as well, yeah, and some biology. So that's what you need. But in terms of a prior knowledge about this area, maybe it's not required. But because these are professional course, you only need the sciences, and you'll be good. And so the history, a little bit of the history, how this uh, 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 area came to develop. So this started in the 20th century. There was a need for analysis of the behavior of soils. The need for the analysis of the behavior of soils arose in many countries, often as a result of accidents. In fact, you've seen in this country buildings collapse, and some accidents I'm sure you've heard or seen in the media. So this used to happen in those. Of course, here these things happen in this age because of negligence. But in fact, in the 20th century, most of the principles were not yet known. So because the railways, all these things that people were trying, the structures that people were trying to bring up were collapsing, and disasters and people losing lives. So because people did not quite understand exactly the principles governing this area, so at the time people died because of the lack of proper understanding. So because of this became a little bit too much, and so scientists or the academics of the time are now thought to research and find out a structured way rather, to tell people of the principles governing this area, some equations or some organized way of design to avoid disaster. So the time, if people don't understand what is happening, then they just, I am sure, if you go in the field, you find some technicians, for example, they okay, there is, if it's a project that has been designed by engineers, usually what is taken in the field is just drawings, but the principles of design are usually not do not I mean, the people implementing do not basically the details of why the drawings are so are not included, so those are probably taken for approval and left as reports in offices. So you hear often some technician just saying, okay, this is how we do things, but there's no explanation, or they cannot explain why. You see, this is the problem. So when you just do things, um, when things are just done, so in that time they were just doing things in a certain way with no proper explanation or no proper understanding. So if you ask them, they say, okay, this is just how we do, this is how we construct a railway, this is how we put up structures. But because of that and the lack of understanding, excuse me, there were a lot of accidents. So then people started doing research to better understand the principles and come up with some design guidelines. So this is what happened. Uh, of course, in the current situation, there's in the country, probably because the disasters happen, there is more understanding of this phenomenon, except there is some negligence of the law and probably the parties involved in the construction. So in the 20th century, there were landslides, failures of foundation, and this part is written in the Netherlands. So in the Netherlands, the slide of railway embankment near, I think, some place called Wesp in 1918 gave rise to the first systematic investigation in the field of soil mechanics by a special excuse me, commission set up by the government. Of course, it's the government's responsibility to protect her people. So if something massive happens at the government, so this accident led to some commission being set. Uh, so many of the basic principles of soil mechanics were well known at that time, but their combination to an engineering discipline had not been completed. So there was no organized way uh, to to run things. So for example, the design codes, for example, so this is the first uh, uh, meeting, or the first organization that seem to organize things closer to the design codes, for example. So the first important contribution to soil mechanics due to Coulomb, with called Coulomb, who published an important treatise in the failure of soils in 1776, and some guy Rankin. So this is gonna be, these names are going to show up in other courses, I think, also very commonly in this topic. So who published articles on the possible states of stress in soils in 1857. In 1857, Darcy published his famous work on permeability of soils for the water supply city in Dijon. So the principles of soil mechanics of continua, including statics and strength of materials, were also well known in the 19th century due to the work of Newton, Kirchner, and Boussinesq. The union of all these fundamentals to a coherent discipline had to wait until the 20th century. It may be mentioned that the committee to investigate the disaster near West came to the conclusion that the water levels in the railway embankment had risen by sustained rainfall, and that the embankment's strength was insufficient to withstand these high pressures. So important pioneering contribution to the development. So this this so important pioneering contributions to development of soil mechanics also made by Tezagi. Tezagi is a very is a household name, so to speak, in soil mechanics, who among many other things has described how to deal with the influence of pressures of pore water on the behavior of soils. This is an essential element of soil mechanics theory. Mistakes on the on this aspect often lead to large disasters, such as the slides Albefan in West, Albafan Wales, and Tetanal Valley. So some of this disaster came upon or came to be due to insufficient understanding of soil mechanics theory. So in Netherlands, much pioneering work was done by Kavelin Boisman, especially on the deformation of rates of clay. So these are so a stimulating factor has been the establishment of Delft Soil Mechanics Laboratory in 1934, and now known as GeoDelft. So in many countries of the world, there are similar institutes and consulting companies that specializes in soil mechanics. Usually, they also deal with foundation engineering, which is concerned with the application of soil mechanics principle to the design and the construction foundation in engineering practice. Some mechanics and foundation engineering together are often denoted as geotechnics. So, the idea here is just to show you how this discipline came to be or came to be organized from experience from different parts of the world, but the motivation or the disasters, because people did a lot of disasters used to happen and people did not quite understand. There were some individual or isolated pockets of knowledge from the Tezagi, from the Boskinesk, from the Darcy and so on, the people we mentioned, but they were not yet organized into one coherent discipline. For example, at the time, to avoid this, these days, if you check the building codes, basically the codes for practice, be it code for design of dams or design of houses because these codes came out because people want to avoid the disaster. So the same thing could happen in this country. For example, a lot of these disasters and people come from different experience or different data, and then they're able to put, because of the experience now we know, for example, that in Nairobi, the bearing capacity for some curtain, because from experience, of course, uh, I say the bearing capacity is so much, and then we put in the design code, in the Kenyan design code, and they say for Nairobi, the acceptable bearing capacity is so much. So you see, you are helping people. So the new people, the new designers can just refer to the code and makes it things much easier. And of course, because from experience, because this has been done for a long time, then people know that if you use this amount of bearing capacity, your buildings are safe. So this is a short story or history how these the excuse me, how this discipline came to develop, which so as how basically the area of geotechnical engineering came to be organized into an organized field. In fact, today the so many the soil mechanics. I mean, under this area, there's so many sub-disciplines that one can talk about. So that's it with the introduction. If there's a question, you can unless there's a question. So because this is the first class, we'll stop here. Although I think this someone is just trying to no, maybe not stop here, because I think the class started a little bit late. The semester is supposed to excuse me, is supposed to have started in August, so these are 2 months late, so I think we can push a little bit. It's the people who are just joining. It's important to attend class early. Please record your attendance, the number and name on the chat box for those who are just joining. So that's enough with the introduction, and so I think we proceed to the next topic just a little bit. So a little bit of the description of the nature of soils. Now, I hope to make it as okay. I hope to make it somewhat simple. Maybe description of the nature of, okay, maybe we use this one, because it appears the PDFs have some writing, which is still fine, but so the so I need you to consider that some my margin. Maybe, I don't know whether this is easier to imagine, or this where there is already some description. Let's see. Okay, maybe here. Okay, we can use this, I think. So imagine some mass of soil as shown. So I use some pointer. So consider a mass of soil with forces F1, F2, F3, F4, and F5. That's the mass of soil, some random mass of soil. And there's some plane there. So you want to know what is happening in that plane. Some angle alpha. That angle alpha could be any angle from 0 to 90, if you so wish. And you load an element of soil, as shown in the in the illustration. Now we are interested in a simple way to, if you wanted to know, because you have loaded the soil and you wanted to know any plane, the effect of these loadings on any plane, this is what we're trying to do. So this is what we're interested in. So this is a simplistic way. We want to derive one formula that can give you, if you're interested in, probably you have loaded the element and you're interested in the plane, the 5 degrees from the horizontal, for example, or in a plane 10 degrees, 20 degrees, up to 90, and so on. So this is the framework. So the formula that we are going to end up with at any point, at any angle, due to a certain specific kind of loading, then you should be able to describe or the stress state at any angle from the horizontal, so to speak. So if you take an element as shown, and I'll try to go slowly to make sure there is understanding. So so if you take an element, of course these forces have to be resolved in vertical and also horizontal direction, because that's the major reference. So excuse me, the forces in orientation have to be resolved in the vertical and in the horizontal directions. So if you make a triangle of forces as shown, so that's the first thing. So with the triangle of forces, and then this is the sign of the sign convention. So the horizontal stresses in this direction are positive, and the vertical stresses up, going up, as shown. I hope you can see the arrow. Please, class rep, confirm that you can see the pointer, the laser pointer, just to make sure we're together. Class rep,
Yeah, I can see the pointer.
the laser pointer. Okay, so this, for the horizontal force, this is assumed to be positive. That means the stresses going the opposite direction are negative, and in the vertical direction this is positive, and the uh, stresses in the opposite direction are negative. And the so for the this is so one thing you need to learn also. So these are called shear stresses. So for example, this is a shear stress, this is also shear stress, which will turn into shear force. So the forces either sorry, not actually, just okay, actually, the shear stresses, okay, let me try to explain. The shear stresses in fact have some relationship. So mm, normal stresses causes shear stresses, if you understand. So where normal stresses exist, shear stresses will exist by default, because one actually causes the other, for this reason. So so normally, I don't know if you've done this, but if this is an element, so an elemental stress, so these are shear stresses, or normal stresses. These are normal stresses. So for equilibrium, this stress, let me use a different pen. So a different color. So these ones are not shear stress. This could be, okay, let's call them normal stresses. Okay, so because of normal stresses, uh, there have to be balancing stresses. So sorry, I think that's not right. Okay, let me erase. So if this is your element, we have to follow the principles of equilibrium. So if the force is there, this has to be in the opposite, like that. Now because of this, these are shear stresses, so in this direction, and this has to go in the opposite direction for equilibrium. Now this makes this element imbalanced here. So because of this, we have shear stresses. So I use a different color to show. So these are shear stresses that are induced because of because otherwise, uh, this is the applied external load. So if it's a load from a building, whatever, so that's the shear. But because the material has to remain in equilibrium, this is the reason for an opposing equal force. Now this action makes these edges not to have any forces, but equilibrium has to be maintained. So because of this, there are shear stresses. So what you should take away from there is that the because of the presence of normal stresses ipso facto induces shear stresses. So when normal stresses exist, shear stresses have to exist. There's no question about that. So all we are trying to derive here is what is the relationship, because normally when you introduce normal stresses, shear stresses will occur as a result. And what is that relationship? So that's what you want to derive from this, from principle. Now maybe you may have known this from structural mechanics. The shear stresses either meet at a point. You can see these ones meet at a corner, either meet at a corner or depart from a corner. You can see, so these ones meet at a corner, these ones depart from a corner, these ones meet from a corner. So those are the characteristics of these shear stresses. So that's just to make sure you understand what you're talking about. So back to uh, so this is positive, and going up is positive. The opposite directions are negative. So for the shear forces, this is positive, and the ones going in the negative in the other direction are negative. And then we assume that clockwise moments, you can see. So we have to consider the forces, vertical forces, horizontal forces, the shear stresses, and the moments. So you can see the moments in this direction are positive. So that is the sign convention for deriving the formula we're going to talk about lastly. So back to this triangle of forces. So let's assume that all these forces, if we resolve them, they can give you a force in the horizontal direction called H. But we need, in fact, we need a force rather than stresses. But in the so remember, stress is force over area. Okay, stress is force over area. So here, this is what we are saying. But assume a unit, assume the area is just one. Area is just one. So per unit area, so all these things, this would be sigma y times 1. You see what we are trying to do there. So if the stress is tau alpha, and the area is 1, that means for unit area, the stress and the forces are just the same. The stress and the force is the same. So that's the point. That's what you need to know. So the no matter the kind of loading, we resolve all the forces to one vertical force and one horizontal force, and we're talking about a unit area. So that's the point. So this that the force which in this direction would be a torque. Of course, you know that shear stresses cause torque. Shear stresses are caused by torque, just like and normal stresses cause moment. So moment is the uh, equivalent to torque, but moments are caused by normal stresses, by normal stresses, which is force over area. So because shear stresses tend to cause twisting, their moment equivalent is called torque. Okay, so because of the twisting action, so the equivalent of moment because the forces, direct forces, with which do not cause twisting, the planes remain parallel, there's no twisting, those will cause a moment. Now the stresses that tend to cause twisting have their moment equivalent called torque, if that is not moment equivalent but force equivalent, sorry, the force equivalent is called torque. So in this direction, this would be the shear stress times the unit area. So if you resolve the unit area along this section is 1, so of course here the area will be 1 cos alpha, and here the area is 1 sine alpha, right? But if the force is sigma in this direction is sigma s, not the force, the stress is sigma x, so the force would be the stress times the area, but the stress is sigma x, the area is 1 sine alpha, which is just alpha, so the horizontal force is sigma x sine alpha. The same idea here. The vertical stress in that direction is sigma y, and the area is just 1 cos alpha, so force times area. I think that should be clear and important. Because of course, and then allow me to preempt, because I think is easy to explain from here, and this is actually very important for you people. So if you can, this is a head, but is easier to explain here without going a little bit. So if you are to draw a force, let me see, not force, but what we are interested in is the Mohr circle, what is called the Mohr circle. So based on what I have told you, we are able to plot sigma stress and what is called the shear stress. Usually it's a nice circle which is symmetrical. So let me change the color. No, no. Let me change the color. So usually it's a nice circle. Okay, I hope you understand that. Okay, usually it's a nice symmetrical circle around the that's not really much change of the ink, but usually this is sigma y, which is called sigma 3, and this is sigma x, and I'm not sorry, so this is not right. This is sigma x, which is sorry, here this is sigma 1, which is equivalent to sigma y. I'm going to explain later. And this is sigma 3. no, this is sigma x, which is the same as sigma y. So that's the essence. So the radius of the circle, would be sigma y plus sigma y plus sigma x over 2. That is the radius of the circle. And no, this is the center. Sorry. So that's the center and 0, and that's the center. So and the radius would be sigma x minus sigma y over 2. So that we get from this relationship. I needed to explain that. And one more important thing is this angle alpha can be measured once you know what is called the pole. So if say this is the pole is here. I'm going to explain that later. So you can just measure the angle alpha there. That is the angle alpha there. So these readings, you see these readings here. This reading here of tau and this reading of sigma are these values. The sigma alpha here and tau alpha there. So all we are saying, you remember I told you that we want to describe the stress state from 0 to any angle. That means you can measure any angle from 0. Once you know the stress state, you can say I want to know the stress state as 10. Once you have the Mohr circle, you just measure 10, then you can read off the stress state. You go to 20, 15, 50, 60, 90, and so on and so forth. So this is the idea, and this is actually what our interest is. So it's beautiful because from this formula, then you're able to describe the stress state in any material. In fact, this is the fundamentals of soil mechanics. This idea is borrowed from structural mechanics as well. So this is the same idea of shear stresses and normal stresses, even in structural mechanics. So I believe that makes things a little clear. So once because of this, the horizontal force, the vertical force as well, and in this plane there's a shear force, and the 90-degree component. So we have the shear stress and normal stress, which I've shown you the relationship in the Mohr circle. So now this one I have shown you the end, but we skip the process because I thought the Mohr circle side by side with this elemental force triangle would make sense. But now to the process, how do we get to the equation of the circle per se? Now I'm going to, because this is a little mathematical, and this here we only need to understand the meaning, and especially the sigma 1 and sigma 3, which is sigma 1 is sigma x and sigma 3 is sigma y, and what they mean in terms of the Mohr circle. There's some math in between, which we will escape because this is not a math class, but the principle is important. So if by now you know that this is civil engineering, so we all need our forces in the horizontal direction to be 0. We usually have 3 equations. The summation of moments should be 0. Summation of forces in the horizontal direction should be 0, and summation of forces in the vertical direction should be 0. Just a moment. Alice, kuna siku aliletwa 208 na utaharakisha. Kuna time aliletwa ama atarudishwa shuleni. Kuna time aliletwa 8 minutes 208, so karibu to 10. So if you you know these three, or you should know. I'm not sure how much structures you've done, but for civil engineering we are concerned with these three. Summation of moments at any point should be 0. This is the other equation. Summation of forces in horizontal direction should be 0, and summation of forces in the vertical direction is 0. The good news is that for this case we ignore moments because of the condition. I think you've been taught about the pin. Okay, I don't know how much structures you have taught, but there are three kind of end conditions or support conditions. We can have what we call fixed pin. We can now have pin support, roller support, and we can have fixed support. All these things have different characteristics. Some of them cannot take moments. This cannot take a moment. Can take forces in the vertical and horizontal direction. This one can only take forces in one direction. It cannot take moments and can also not take some forces in one of the either x or y direction, depending on the direction of the roller. A fixed end moment can resist all the forces. So because of this kind of support conditions, you can make some of either moment may be 0, or some forces should be 0. So in the soil, because of the nature, the interaction of the soil, we assume soil is a pin. So if soil is a pin, that means moment is 0, and so that's why you see the equation for moment is missing. I hope that's a sufficient explanation. So here we are supposed to use the three equations, but because of the support condition of the soil, the moment forces do not exist. In other words, we assume the soil cannot take moments because of the nature or the way the soil is. So that's why we only use these two forces. So from the excuse me, from so from equilibrium of forces, the I think I don't need to tell you the you should know this how to resolve forces from physics. So this and that, you can see the component of this is negative, and the component of that is also negative. So that is the reason why you see this is minus, I believe. Yeah, so the component of n is negative, and also if you were to, I think, resolve this, sorry, here, you can also see this is negative and this is positive. So explains why this is here is positive and that's negative. So in other words, you just sum the horizontal forces, you resolve, and then sum the horizontal forces, you resolve, and sum the vertical forces. I think I couldn't get clearer than this, and I've spent quite a deal of time. Just make sure we're together. Class rep, please confirm that unless someone has a question. I hope it's clear. Class rep, I need your confirmation.
Yeah, it's clear.
Yeah. So because this is a fundamental principle that needs to be well understood. So so after you navigate all these the stresses, how to convert the stresses to the forces, then you only do what you call the resolve the forces. Summation of forces in the horizontal direction is zero. So you need to resolve the n and t components, which I've shown you how to do, and then you sum. So this is horizontal, you can see is here, and then this component is from this, and this component is from that, and you also need to pay attention to the detail. Okay, but these are forces, so you need to convert them into stresses, basically by dividing by one by one, because the area is one. All right, so you can see here, or not really, the you just substitute, because the H force, this is sigma times the area, so the force, but now you write the force out in detail. So H, you can see H here is sigma x sine alpha, so here sigma x sine alpha, and then T cos alpha is the same here. So because T is tau alpha times 1, so tau alpha times 1 is just tau alpha, so this is where you can see tau alpha cos, and then sigma alpha cos sine alpha. And then also need to pay attention to this. You can see the sign has changed. You can see the sign has changed, and this has something to do with the convention of the force. I think you can do the mechanics, mechanics in your free time. But at the end of the day, now when you substitute, so these forces, this you substitute the actual values here and there. So the equation from equation 11.1a, you get equation 11.2a. From equation 11.1b, you get equation 11.2b. Now, I think from my explanation, you can go home around to actually see that you can get these equations that we're talking about. And I've spent a great deal of time trying to explain to make sure you understand. So again, now, so this is the same thing that I've explained, but now in words, just to make sure there is complete understanding. So consider a soil mass that is acted upon by a set of forces. Excuse me. F1. I think that's clear. So I'll just read if there's a question you can ask. So F2 up to Fn, as already shown. I think I've spent a lot of time trying to explain. For the time being, let us assume something is not right. Let us assume for the time being, just a minute, let us assume let us assume, okay, some problem there with the some problem there with okay so let us assume that these forces act on the soil and acted upon by a two-dimensional plane. I think I've already explained this. We could resolve these forces into components on small element at any point within the soil mass. Such a point or in the figure. So this, and we assume the center, and this element, this center O, now O is here, and then we assume the triangle of forces, and the resolution of these forces into normal and shear components. I will explain this. Acting, for example, on a plane passing through point O at an angle from the horizontal is shown in figure 11.2a. 11.2, I'm not sure which one of them is. Okay, this is also reproduced here. Just so this is 11.1, 11.2. So which is an expanded view of the small element at point O. Note that for convenience, our sign convention has compressive forces positive, because most geotechnical engineering forces are most normal stresses in geotechnical engineering are compressive. So here we assume compressive forces are positive. It's just a sign convention, but I'd suggest you stick with this, because otherwise the if you don't uh, stick with this, then the sign convention might confuse you. In structures, you study more or less the same things for you study more or less the same things, but the sign convention is a little different. So so please note this, but you keep the sign. This is just a sign convention. You can assume, even if you assume something else, an opposite direction consistently, you should arrive at the same solution. So requires that positive shear stresses produce counterclockwise couples on our element. This is idea was by Parloff and Baran in 1976. So put another way, positive shears produce clockwise moments about a point, just outside the element as shown by the inserts by figure 11.2. And clockwise angles are taken to be positive. These conventions are opposite those normally assumed in structural mechanics. I think I've said this. To begin, assume that the distance C along the inclined plane in figure 11.2 has a unit area. I think we've talked about that as well. So this is just to elucidate the point further. So I think with these diagrams and the explanation at your own free time, you can see. So we assume this is a unit area. So uh, so so that the figure has a unit depth in the particular perpendicular direction to the plane of the paper. Thus, the vertical plane BC has the dimension of 1 sine alpha, and the horizontal dimension AB has equal to 1 cos. I think this is what we are trying to explain the area. So if this is 1, and this is 1 cos alpha, you should know this, and this angle is alpha, and this is the area. Sorry, the area here BC 1 sine alpha, and area BA is 1 cos alpha. That's what this is trying to explain. And at equilibrium, so the summing of horizontal, I think basically this is an explanation of in detail of what I have said. And then you divide the forces in equilibrium by the area upon which they act. We obtain normal shear. So this is the so these are the equations expressed in terms of forces, and these are the same equations expressed in terms of stresses, and we divide by the area. And I need you to notice here that this was positive. Now the division has changed the direction of the stress. So this is a force. While it is a force, is positive. The area in this direction seems negative. So therefore, the you can see the direction of the stress now is negative. Now this is the simplest way to derive this point. Of course, we are going to skip a great deal of mathematical manipulation, which you don't need. In fact, you only need to know how to reach these equations, like I've explained, and then the solution, because the in between, that is mathematics. Of course, you need to know, because I'm sure you do a lot of mathematics in civil engineering. So somehow you should be able to figure out how the answers are obtained. A hint is from trigonometric identities. Just to give you a hint, for example, these are two equations, but we need to express them in terms of sigma x and sigma y, because that's the most important thing. So solving the equations 11.2a and 11.2b simultaneously for sigma x and tau x. Sorry, not yeah. Because we are interested in the plane. Remember here. Okay, I'll give you a hint. Normally we know. So we are interested in the stresses in a plane, because that's the most important in any plane. So that if you load a material at any point, you should be able to tell what is the stress state, the normal and shear stress. And I've told you normal and shear stress always go together. So if there are normal stresses, ipso facto there are shear stresses. So you need to know the normal stresses on a plane and shear stresses on that very plane. You only need to know the angle. Okay, so the so these are two equations and two unknowns basically, whichever way you solve, these are the solutions. Okay, just a minute, guys. Baba nafanya kazi, hebu wacha ni nini. Pole, fanya homework, alafu nitakupatia remote na simu, sawa? Sawa, wacha nifanye kazi, alafu nitakupatia simu, sawa? Nitakupatia remote, sawa? Na so this is the solution, in fact, for the equation. And this, in fact, you remember the solution for a circle. I'm sure your memory from high school should be much better than mine. That you are x minus a squared plus y minus b squared equals r squared. This is a circle whose center is AB and radius r0. That's the point. In fact, I think I'd already hinted. So the interestingly, if you solve those two equations accurately, you have a circle whose center is 0 and sigma x plus sigma. I think I may have misrepresented this before. Sorry. So this is not accurate. Sigma x plus sigma y over 2. That is the center. That is the x coordinate 0, and the radius, in fact, is sigma x minus sigma y over 2. So this is where we are headed, and if you solve that equation, that's the point. And in fact, this is what is defined as the Mohr circle, and this is what we are trying to explain, such that if you draw your Mohr circle here, and you know what is called the pole, from the pole you can measure any angle you want, and from here you can read. So this is tau and this is sigma. From here you can read any tau alpha and sigma alpha. That's the point. So that's the whole point of this Mohr circle, and is important because you are able to get the stress state at any point. And of course, what is important are the here is sigma y plus sigma x over 2. That is the center, and the radius here, the radius there is sigma x minus sigma y over 2. Now sigma x is usually just called sigma 1. It's gonna be very common, and sigma y is called sigma 3. I'm going to explain that in a while. So that, I think this is a fundamental principle that please make sure you have understood very well. And so this is just to explain what we are trying to do. So I know in my explanation I said that the pole can be here. Actually, the pole can be here or can be there, and you can see that the circle is actually symmetrical. So you only need to know what the pole is, which we'll define later. Then from the pole you can measure the angle, and you can see you get sigma alpha and tau alpha, and any angle you want, if it's 10, if it's 20, if it's 30, 40, 50. So that in a nutshell is the beauty of this Mohr circle. And so this is a 2D plane, while in actuality we have 3D. In actuality we have stresses in both x and in y, and it would be difficult to express this in 3D. So this is a simplified way. So usually this is sigma 3, this is sigma 1, and this is called sigma 2. And because in reality we have 3 dimensions, not 2 dimensions, so this is usually the least, this is the maximum value, and this is in between, so we call it intermediate. There. So sigma 1 is called principal stress because it's the maximum major principal stress. Sigma 3 is called the minor principal stress, and sigma 2 is called the intermediate principal stress. The values I've shown you, and this is the next figure is shows you the relationship. So this is how the circles are supposed to be, but to make it easy, because again drawing circles like this would be very complicated. So to make it easy, we just take the maximum and the minimum, and we are able to get a nice circle which contains the two of the actual circles. And of course this would be an overestimation, but the design resulting from this would be safe anyway, because you can imagine how complicated it would be if you are to draw this circle. So this is the least, the intermediate, the maximum. So if you are to draw 3 circles, it would be more complicated. So not 3 circles, but 2 circles, it would be more complicated. But now to make it easy, just take the maximum and the minimum and you draw 1 circle. But you can see this circle contains these other 2 circles, so it's still okay for the purposes of what we are to achieve. So this is just to show you now what to do. So these things, this usually done in a test. For example, shear test, or we call it direct shear test, or this what is also called the triaxial test. So because we always know these values, but what we don't know is the stresses in any other plane. So by drawing the Mohr circle, you can determine, and in fact this is very useful in understanding the principle of Mohr circle. It's very useful in understanding the excuse me, the stress state. Now you should also note that the scales in the vertical and horizontal direction are usually the same scale. So if this is 0 to 10, this from here to here also has to be 0 to 10. The scales should be in a ratio of 1 to 1. Please note that. So this is it. Now you can use in a nice graph. So this is one exercise for you. And remember, now I remember what I told you. If you are given an assignment, please do it. And this is also just the procedure of how to do it. So actually there's not much of demonstration, but you can see now how this applies. I hope I'm not sure that I did demonstrate. Okay, here I've shown you how to, and the procedure there. You can do that, and then you try this by yourself. Of course, if you have any problem, you can let me know. Uh, okay. So the key points which I've talked about, in fact, but maybe it doesn't hurt to highlight. This a pole is a point of non-stress. Maybe it's better to explain from here. Uh, so if you're able to draw the Mohr, in fact, okay, let me demonstrate here. Actually, there's nothing to even to demonstrate. Is would be very easy. Same scale. So I expect you here, the tau, same scale, and sigma, same scale. You plot sigma. You plot here 52. 52 there, and you plot 12 there. All right, and you draw your Mohr circle. It's okay, a half circle, because you can see the circle is symmetrical, so you can draw a half circle or a full circle is okay. And then the the pole is point of non-stress. That's a point. So point of non-stress, you know that sigma 1 sigma 1 is 52, and you also know that sigma 3 is 12. Now when there is major principal stress on this when so sigma 1 is the major principal stress. At that point, tau is 0. Again here, tau is 0. Because you can see the plot here and there. So in the major principal planes, on the major principal planes, the shear stress is 0, no doubt about that. So, and these things are symmetrical, so it doesn't matter. So one pole is here, one pole is there. So you can draw, if you want it to know 35 is the same there. No. I think that's wait. Okay, just a minute. So once you draw your Mohr circle, I'll leave that for you. Once you determine the pole, you measure the alpha, and this becomes your sigma alpha and tau alpha. But the point is, pole is a point of non-stress. So once you know the stress, you locate it at the on the Mohr circle, and that becomes your pole. So that's the definition I wanted to define. So the pole is a point of non-stress. Now, major principal stress is the maximum stress acting on the major principal plane. So two things. I think the simplest I can put it is this one. Is this way. So this is the major principal plane. This is sigma 1 is the major principal stress, is the maximum, and it acts on the major principal plane. So this is what we are saying. Then this is minor principal stress acting on the minor principal plane and is the least, and this is called the minor principal plane. And this is intermediate principal stress, acts on the intermediate principal planes. The planes are 90 degrees to each other, and so I don't know. So sigma 3, to put it in more mathematical terms, is less than sigma 2, which is less than sigma 1. Or if you want, sigma 1 is greater than sigma 2, which is greater than sigma 3, whichever way. So you get the idea. So that's all the explanation that is there, and I hope that gives you a very good idea of what we are talking about. Now, I think I will end there because there's too much information, and I've tried my best to make sure that you can understand. Unless there's a question, class rep, I will end there and we proceed from there next time. Comments? Class rep, is that okay? Unless there's a question.
To me, it's okay. It's okay right now.
Okay, so meet see you next week for the class.